Good morning. Today is isomerism part 2 lecture that will cover or entirely focused on optical isomerism. So today we are going to study optical isomerism. Now what is optical isomerism? Optical isomerism is a very beautiful concept. We already know what are isomers. Isomers are two molecules having identical molecular formula but different physical and chemical properties. In case of optical isomers, two molecules having same molecular formula, identical physical and chemical properties. Then what is the point of difference? They differ from each other only with respect to their behavior towards plane polarized light. Now, what is plane polarized light? A light in general that we have around us from sun or from tube light or from bulb or any source of light travels in infinite possible planes. But if I pass it through some polarizer, then it will allow only those waves of light to pass through it which are in one plane and will function opaque to the rest of the light radiations. So the resultant light after that polarizer is called plane polarized light. And when this plane polarized light passed through our molecule, which we call is optically active, then the plane of the traveling light will be either twisted towards the right or the left. So our molecule is having impact on the plane of this light. Okay, so if I have an optically active molecule, one molecule will rotate it to right hand side, the other will rotate it to left hand side. Now what is that other I just said? Let me show you something. See, this is a chiral molecule. Now what is this chiral or chiral molecule? Center you take carbon. These are the four different groups I have attached to four corners of tetrahedron. Okay, let me show you its mirror image. I hope all of you can see this molecule is mirror image of my right hand is mirror image of my left hand molecule. Okay, so these two seems to be identical if I don't place them like this, if I don't study optical activity of these molecules. If I'll hide this and then we'll bring this, you will say that it is same molecule, I am just jumbling between the two. No, they are two different molecules. And what is the check that they are two different molecules? Superimposability is the check. If I'll place this molecule on this, then a condition should be white should come on white, purple should come on purple, orange should come on orange, and green should come on green. But as you can see, any two will come on each other, but the rest will have a problem. Including carbon, I'll reframe my statement. Any three will come on each other, central carbon and any two substituents. In our case, we have said purple, purple, and white, white. But see, green, orange are not superimposable. Whatever you do, whichever way you want to present it, that no, I can superimpose these two. If you will have any other two, you will lose the rest. It is never possible that all four of such molecules, all four bonds of such molecules will be superimposable on its mirror image. So when a light, plane polarized light, passes through this molecule, then if electromagnetic field of this molecule rotates that plane polarized light in a right hand direction, say by 5 degrees, then its mirror image will do the exact rotation but in the opposite direction. Because as you know, the vectors of the two mirror images will be identical but in opposite directions. So these two molecules, which are non-superimposable mirror images in our hand, are chiral molecules, are optical isomers because they will have exactly same IUPAC name till now, whatever we know. They will have same physical and chemical behaviors. They will have identical reactions, most of them, but will have only difference towards the plane polarized light. So such molecules are called optical isomers of each other, and the phenomenon is known as optical isomerism. Okay, a very common example in the books about the superimposability is these hands. They say right hand is mirror image of left hand, and then they say we superimpose. So I guess all of you must have got a misimpression that for superimposition you have to put just exactly like this. Most of you feel, can I not make it like this? Now it is superimposable. Okay, so let me tell you, you are allowed to rotate the molecule, rotate the hand for check of superimposability in all possible directions. No limitation to that. But your interpretation that this namaste pose is superimposability is wrong, because the word superimposability will be applicable when I come to have nail to nail positioned, skin to skin, palm to palm, and everything finger to finger. So when I do this, you can see my thumbs are not superimposable. You can see my overall arrangement, the which finger on which setting is not superimposable. My little finger is on my index finger, and all this is not right. Okay, so even in case if you think that the we were not allowed to do this way, otherwise you could have attained superimposability. I hope now you're clear that no, you can do this, whatever you like, but superimposability will never come, because it is never going to be a case of nail to nail, finger to finger, skin to skin, all possible superimposability. Okay, so considering all these facts, it is such a vast branch of chemistry that is optical isomerism, and is very important in today's context of exams as well as our day to day life. How? Because the drugs, the medicines, the different types of things that we consume usually function on our body in a very lock and key method. If you check most of the structures that we consume, any drug possible you take, 95% of them will have a chiral center. 95% of them will behave overall optically active. And then if you check that only one type of isomer of that medicine, of that drug, is used to treat us, whereas in case if just by even error it's another isomer, it's enantiomer or it's tristereomer, enters into the sample as impurity, then the whole batch is to be suspended, is to be thrown out. Because you never know that if a dextro is working on your body as a medicine, it functions on enzymes, it functions on various biochemistry centers in our body. If a dextro is working as a drug, a levo may be poison. You never know. You cannot take the risk. So, living system is highly sensitive towards the type of optical isomer that we need for a particular process and that we need to be consumed. So there it is a vast discussion. I can go on and go on saying about optical isomerism. Let's come to the theory part, which will directly influence our IIT syllabus. Again, I would say I'll try to limit myself as much as possible in the limits of the JE syllabus. Otherwise, this topic is, very vast. So let us start optical isomerism. I have already told you what is optical isomerism. The two molecules which are identical in physical and chemical properties, but the only difference between the two is their behavior towards plain polarized light. Then those two isomers are called optical isomers, and the phenomenon is known as optical isomerism. To represent these molecules, we use certain representations, say wedge dash. For wedge dash represent, we keep a tetrahedron in a plane of paper such that, including the center atom, other two atoms are also in the plane of paper. Okay, overall three are in the plane of paper. Under such a visualization, the rest two will move in and out of the plane of paper. I am talking about the variables, I am not writing any specific atoms. C and D. Okay, so this representation is called dash. This representation is called wedge. Wedge is towards us, approaching the viewer. Dash is behind the plane of paper, and these simple lines are representing within the plane of paper. Its mirror image can be represented as C, A, B, and D. Okay, the other representation that we'll use is Fisher representation. In Fisher representation, we always keep longest carbon chain on vertical line. Okay, we keep longest carbon chain on vertical line. Now let me tell you that what does this vertical line represent. Okay, in a Fisher, vertical line will represent bonds directed away from us behind the plane of paper. Okay, horizontal line will represent bonds directed towards us. Okay, so if I say here, if I want a viewer is set here and he's observing this, then the Fisher of this first representation will be A, B, C, and D. Okay, A, B, C, and D. Fourth point, carbon with highest oxidation state is placed at the top or closest to the top. Either you place it exactly to the top or you place it closest possible to the top. That is fissure. Okay. For example, if I have glucose, see, glucose is always written in a conventionally correct fissure like this. This is the conventionally correct fissure. If you see, the longest carbon chain is placed on the vertical line, the highest oxidation state carbon on the top, rest all are right left, right left. These right left will be coming towards us. Vertical will go behind the plane of paper. If it is fructose, you cannot place the highest oxidation state on the top. then also it is okay. If you cannot place it on the top, then you will place it closest to the vertical top. Now, these are the conventional rules. Let me write the word conventional. These are the conventional rules. But when you deal with the question, don't expect that they'll follow only the conventional rules for this particular writing of a Fisher. Because when you are creating an options, in options, it could be one following, only one could follow the convention. Na? Other options will be created, will be generated only by not following the options. Okay, so there is always a possibility. Please don't wait that all the structures will follow the conventions. Now, how do we come to know that a compound is having this amount of optical activity or that amount of optical activity? So what we do is we use an instrument in the lab called polarimeter. Polarimeter is basically, if I say I am using some source of light here, source of light here, then there is some, say, setting of Nicole prism in this. My light is passing through this. So this is my polarizer. Take. After this polarizer, just as a rough sketch I'm drawing, only light traveling in, say, this direction is allowed, and for rest it has function as opaque. Now I have a polarimeter tube. I have a polarimeter tube here. This is polarimeter tube. This is our plane polarized light, PPL. In this polarimeter tube, we fill the solution of known concentration but whose optical activity is under study. Okay, so this is solution of known concentration of the CPD's compound under study. Okay, now after this there is a observing lens. When we move after that, there is a observing lens. Observing lens has proper gradations, has proper markings. It has proper gradations and marking. Okay. And here is the savior. Viewer observing lens. Okay, so when our PPL comes from this, so first we set our polarimeter in the start without this solution. Okay, and we mark that position as a reference scale 0. So first is without solution or compound, pure solution, and mark maximum brightness position of observing lens as 0. Okay, then we fill polarimeter tube and again start setting this particular observing lens for this observer. We will reset in a particular position of maximum brightness. Okay, if to obtain the new brightness our observer has to rotate the observing lens in right hand side, then he will report that the compound in this polarimeter tube is dextrorotatory, right-handed rotation. And if he has to rotate in anti-clockwise direction towards left-hand side, then he will report that this solution under study is behaving as levorotatory. It is rotating the light towards anti-clockwise direction. Is it okay? Correct. So let me, usually we always say that when the compound rotate the light in clockwise or anti-clockwise, but in what reference? So that reference is always with respect to the viewer. Okay. So if the light is rotated in clockwise direction, और हम इसे राइट हैंडेड भी बोल सकते हैं, राइट हैंडेड, then the Latin words are used, then it is called dextrorotatory and is represented by small d. Never ever, even by error, represented by capital D. That is entirely different thing. If you have to rotate this lens in anti-clockwise direction, or you can say left-handed rotation, then it is called levorotatory or small l. Okay. And the third condition that you may think, if there is no effect, if there is no effect, then the compound is either, okay, if there is no effect on light, then either it is optically inactive, it has no special behavior towards the PPL, or is a racemic mixture taken. We'll deal with this term in the later half of the lecture. So now those compounds which behave, which have some effect on the PPL that we just discussed in the above polarimeter experiment, what is their characteristic behavior? What is the characteristic structure that results in that optical activity is actually the chirality or the asymmetry. Now we can have a complete lecture on this particular term, chirality or asymmetry. But to cut it short, all I would say is such molecules which are non superimposable on their mirror image, on their mirror image are called chiral or asymmetric. Today, at the start of lecture, I shown you those two models. Please take them as a reference here. You can go back to reverse and relate to this, that they are non-superimposable mirror image of each other. Okay, now what I'm saying, you relate to this. This is important points that I'm now making. And students usually are confused with these also. I would say with these only. For a molecule, number of chiral centers for a molecule to be chiral. For a molecule to be chiral, minimum number of chiral centers should be answer 0. There is no particular requirement. Now, what is chiral center? This term chiral center is tetrahedral center with four groups different. So even if a molecule has no chiral center, it can still be chiral. Okay, हम example लेते हैं. Let us take an example of this point. We you know already, but you might be forgetting. Remember the allenes A, B. In our that day lecture, previous week lecture, I made which way. I'll try to repeat the same so that you can relate the logic. They were in perpendicular plane. If you take its mirror image, if you take its mirror image, it is a non-superimposable mirror image. So these are chiral molecules. These are chiral molecules. But you ask how many chiral carbons, chiral centers are there in this molecule? And how many chiral center? Then answer is 0. There is no chiral center in this molecule because for a chiral center, first condition is a tetrahedral center. All the carbons are sp2 hybridized. Okay, so first thing is for a molecule to be chiral, no need to have compulsory presence of a chiral center. But yes, if a molecule has one chiral center, okay, if a molecule has one chiral center, then it will be chiral or not? Answer is yes, chiral. If it has only one chiral center, then it will be chiral. Okay, if I repeat the above question, if a molecule has two or more chiral center, then it will be chiral or not? Then my answer will be depends. It could be, it could not be. If it has two or more chiral center, then it could be chiral, that is non-superimposable on a mirror image, or it could not be chiral. It depends. Depends on what? Depends on configuration of those chiral centers. Okay, so let me conclude what I just said. A chiral molecule is the one which has a non-superimposable mirror image. Okay, if a molecule has minimum one chiral center, yes, it will behave chiral. But if it has two or more, then it could be chiral, it could be a chiral, depending on the configuration of the rest of the uh, other chiral centers. Yeah, all the chiral centers. Okay, and the minimum number of chiral centers required for a molecule to be chiral, answer is 0. It can be 0 and still it is chiral. Now I cannot go much to RS nomenclature because it is not in the JE syllabus as so, but it makes a little ease when you are asked to identify which of the structures are enantiomeric, diastereomeric. So just brushing, yes, RS nomenclature. It is the IUPAC nomenclature of optical isomers. For it, we use something called CIP rule. Okay, CIP priority rules, which is Kahan, Ingold, and Prelog sequence rules. Kahan, Ingold, and Prelog sequence rules. Okay, so using this RS nomenclature, we will visualize the tetrahedron such that as per CIP, if the lowest priority group, okay, if the lowest priority group, say fourth priority, say first priority, say second priority, say third priority, okay, if the lowest priority group is directed away from us, then the rest of arrows, if we move in a decreasing order of priority, If they go anti-clockwise, then the isomer is said to be S. Full form is sinister, meaning left-handed S isomer. C. Its mirror image. First priority, second priority, fourth. This will be its mirror image. Automatically in a mirror image, this is going right-handed. That is rectus. So how you assign? You arrange the four groups attached to chiral center as per CIP, Kahan-Ingold Prelog sequence rules. Visualize the tetrahedron such that the lowest priority group is directed farthest away from us. And then for the rest three groups, you draw an arrow in decreasing order of CIP priority. Okay. If that arrow is clockwise, then the molecule is said to be R isomer. If it is anti-clockwise, then it is said to be S isomer. Okay, if a molecule is chiral, then it always have these two in nature. Okay, I hope I'm correct. I hope I could help some. Now coming to different type of optical isomers and terms that we are using. Okay, so what we are using? Enantiomers, type of optical isomers. So first we are moving to enantiomers. These are the most basic that we just studied. Enantiomers are non-superimposable mirror images of each other. Enantiomers are non-superimposable mirror images of each other. Okay, so they will always exist in a pair. Yes, in an enantiomer, as a rule, in an enantiomeric pair, if one molecule is dextrorotatory, small d, then the other molecule will be levorotatory, small l, compulsorily. Then the other molecule will be levorotatory. In an enantiomeric pair, if one molecule is dextrorotatory, then the other molecule will be levorotatory. That is a rule. Okay. In an enantiomeric pair of molecule with only one chiral center, or abhi to I'll limit myself to only one chiral carbon, then in one isomer, the chiral carbon is in R configuration, then in other it will be in S configuration. Okay, but I would again emphasize on the point that this second point, first point is valid for all types, but the second is valid only when it has a one chiral carbon. Okay, If one is dextro, other is levo. If one is R, other is S. But important note, no correlation between R to dextro or to levo, S to dextro or a levo. This RS is our way of saying clockwise, anti-clockwise by assigning some priority and all this. This dextro levo is nature's way of saying clockwise, anti-clockwise. There is an interaction of electromagnetic field of light and the molecule. So no, it is not fixed that an R isomer is going to be levo or a S isomer is going to be dextro. It could be any which way. An R has a 50% probability of a levo or R could be dextro. Please mark this in your brains very firmly, very importantly. Don't make mistakes with this. Okay, a molecule could be R, could be S, and it could be dextro or levo. There is no fixed thing that if it is R, it has to be dextro. Similarly, an S isomer can be dextro, can be levo. There is no correlation. Okay. If, let me come to my next point, we made some important conclusions. Let me mark those. If a molecule has two chiral centers, if it has two chiral centers, so possibilities of its configurations could be RR, its mirror image will be SS, RS, its mirror image will be SR. Okay, let me just write it first. I have two chiral centers, then this is how it will behave. Now in this two chiral centers, point number A, if I number them as 1, 2, 3 and 4, if molecule is symmetrical, then 3 and 4 are identical. I'll show you. If molecule is unsymmetrical, then 3 and 4 are enantio. Okay, it entirely depends on the arrangement of the molecule. Okay, so let me again take that risk that we have taken yesterday also. I'll again do. I'm coming to this mesomer. To have that mesomer, I need you to see this. Okay, as you know that R will cancel out the activity of S. Now, if that R is within a molecule and is of same groups, then what will happen? So let us go here. See this. This is 2 chiral carbon. Okay, I have attached it to white, blue, green. Similar things I have attached other side. Okay, white, blue and green. Similar things we have attached this way and that way. Now, yesterday we did confirmations. So about this bond, this molecule can rotate. In one of the eclipsed confirmation, okay, in one of the eclipsed confirmation, you can see one half of the molecule is mirror image of the other half of the molecule. I don't have to go for the other. Whereas previously what we were doing is one molecule is mirror image of other. A light passes through this, rotates clockwise 5 degrees, and this another molecule brings it down back to anti-clockwise 5 degrees, and net effect if it passes through both, become 0. Whereas in this, a light passes through this molecule starting from first chiral center. If first chiral center had an effect of, say, dextrorotatory by X amount, it proceeds further, moving to this next chiral center. Then this next chiral center will bring it back to its original position because it will do the same amount of optical activity as the first, but in opposite direction. So the net effect for the light when it passes from whole of this molecule, and when I observe here, I'll say, oh, there was no effect. Are you getting my point? That the molecule is having two chiral center, but still, due to its own arrangement, it is still behaving as optically inactive. Okay, so such molecules are called mesomers. It is not that always it is going to be same. Just imagine if this blue and white, I interchange in their position. If I just interchange this blue and white like this, now they are not going to behave as mirror image. Oh, I did the same thing again. I will change. Now see, one half is not acting as a mirror image of other half. If I want to bring this, then something else will be problem, something else will be problem. So this structure will behave as optically active. Okay. But if I change, then again it could be optically inactive. If I change one blue with red, then whichever position they could have been, they are never ever going to be intramolecular cancellation because they are two different groups. One is blue, one is green. Sorry, one is blue, one is red. They will never cancel out each other. So such molecules in which the groups attached to these are different, they will never form a mesomer. Okay, and there is no rule that for a mesomer there has to be only uh, what should I say, there has to be only even number of chiral centers. Okay, there could be more chiral centers, there could be 3 chiral centers also, which could give us a mesomer. Let me show you. I can have a molecule with 3 chiral centers and it can behave as a mesomer. Give me just 1 second. I'll put one here and a green here. Let me see. Can you see? I have arranged a molecule with 3 chiral centers. Okay. Now I said this molecule will also act as a mesomer. How? This central carbon, if I pass a plane passing through the center carbon, cutting it into 2 pieces like an apple or a lemon, and proceed that plane down, that plane will function as a mirror image now. White ka image, white, black to black, green to green, blue to blue. So for a molecule to be mesomer, okay, for a molecule to be mesomer, it can have even number of chiral centers or odd number of chiral centers. Both are allowed. Okay, so let us go back to our theory. I hope this would have given you a clear view what exactly the word mesomerism mean for us. Okay, otherwise you always limit yourself to only chiral carbon with even number. That is not true. So now let me conclude. What are mesomers? So I would say molecules with 2 or more chiral centers but still behaving optically inactive due to presence of symmetry elements like POS, plane of symmetry, COS, center of symmetry, etc., are called mesomers. Okay, are called mesomers. Tartaric acid is a very famous example of mesomers. See, this is a fissure. This plane is acting as a POS. If you take its mirror image, it will be superimposable on our structure. OH, OH, H, and H. If I change it a little here and there, H, OH, OH, H, COH, COH, HOH, OH. So this will be our enantiomers. These are identical and are mesomers. Okay. So in mesomers, there is internal compensation of light. Which light? PPL. That it was rotated, but net result is coming as zero effect. Okay, within a molecule it has been compensated. I hope I'm clear. Now I would like to first go to the word racemic mixture. In case of racemic mixture, equimolar solution of two enantiomers is called racemic mixture. Equimolar solution of two enantiomers is called racemic mixture because, again, the same way, if one will rotate the light in clockwise, the other will rotate in anti-clockwise direction. So overall, the light remains undeviated, and therefore, overall activity of the solution is zero. So racemic mixtures are optically inactive. Racemic mixtures are optically inactive. But why? So due to external compensation. The word external because the light moved into first and then had some effect, but when moved into another molecule was net zero. Whereas in mesomer, it was the internal compensation because for net effect, it didn't have to go for outside the molecule. Within the molecule, its effect is brought zero. Okay? Is that clear? So mesomer is a type of intramolecular racemic mixture, whereas racemic mixture is when equimolar mixture of the two enantiomers is taken, then the overall activity of the molecule being zero, okay, is called racemic mixture. Let's move to next definition called diastereomers. Now, first of all, be very clear that diastereomer word is not limited only to optical isomers. Diastereomer is any two stereoisomers. Any two stereoisomers. कोई सा भी हो stereo. So bracket में I'm writing it could be GI or OI, both. So any two stereoisomers which are not mirror image of each other are called diastereomers. They just have to be not non-mirror image of each other, whether they are geometrical, whether they are optical, they are all are called diastereomers. For example, if I say cis-2-butene and trans-2-butene, they are not mirror images of each other. So they are called diastereomers. Okay. If I have COH, COH, HOH, HOH, the meso to any in the enantiomeric pair. Any in the enantiomeric pair, then this is a diastereomeric pair. So any two stereoisomers which are not mirror images of each other are called diastereomers. It could be geometrical setting, it could be optical setting. Okay. One thing I would like to add, two diastereomers have different physical and chemical properties. More important पे stress no, that is different BP, MP, water solubility, etc. Okay, so they can be differentiated or separated by distillation, etc. Okay, but as I was repeatedly saying, but enantiomers have same physical properties, so cannot be separated by usual methods. Cannot be separated by usual methods. Enantiomers have same physical properties, so cannot be separated by usual methods. For them, we'll need some different and specific methods. Okay, and how they to be are they are to be separated? Let me go to that. Resolvable. Let us resolution. Resolution is method of separation of two enantiomers from racemic mixture is called resolution. Okay, method of separation of two enantiomers from racemic mixture is called resolution. Now it is very tough because they have no difference. How will you separate them? They have similar chemical, similar physical properties. Okay, so we do it by converting them to diastereomers. We do it by converting them to diastereomers. For example, if I had to separate 2 butanol, let this be this one isomer of 2 butanol. Okay, other isomer of 2 butanol is CH3OHH. Now I had this mixture, both of them were present. Okay, so this is S isomer, R isomer. This will be S isomer. In a racemic mixture, both are present. I will treat it with optically pure. Okay, optically pure, either R or S. Either R or S, chiral carboxylic acid. Not all. You cannot take it all possibilities. Either R or S. So let me take CH3H C2H5 COH. This is 2-methyl butanoic acid. Okay, 2-methyl butanoic acid, and assume that I have taken its R isomer. So when the reaction, what reaction will take? Acid plus alcohol will form ester. When the reaction will take OH of this, H of this will be gone. There will be no effect on these chiral centers. They will remain intact. Okay, so in the product of this, in presence of H2SO4, I will treat. So in the product, I will have 2 esters. What will those be? CH3 HC2H5 COO. Okay, I'll change it to say CH3 C2H5 okay, H is on this side, O is on this side, and it is still is an R center. So in this, the 2 chiral centers are R and R. Now let me draw one more. CH3 H C2H5 COO H C2H5 CH3. This is an R S configuration. Now I can clearly see these two are diastereomers. Okay, so now I will separate it by distillation. Distillation one and other. RR in one container, RS in another container, because they will have different boiling points. Now I will hydrolyze. Okay, R acid plus R2 butanol, R acid plus S2 butanol. Now I will do, as one is acid, one is butanol, I can do distillation. If required, you can have a fractional distillation depending on the values of their boiling point. One side I will have R acid separation, and I will be able to separate finally acid and alcohol. Similarly here, R acid and S2 butanol. So yes, it took a very long method. It was not directly that you just put the mixture in a distillation or a crystallization compartment and you get the result. No, you need to convert them to first diastereomers. And then you have to do such a long method. So resolution is a method of separation of the two enantiomers from racemic mixture, and it is relatively very difficult. Okay, it is relatively very difficult as compared to the usual methods. Okay, it is because they don't have the same physical and chemical properties. If they would have had the same physical and chemical properties, it would have been easier. But it is not so. Okay? Similar one term comes is resolvable. What is the term resolvable? Resolvable when we can separate two enantiomers from the given mixture. Then we call it resolvable. Okay? When you can separate the two parts which are cancelling each other. Now, mesomers cannot be resolved. Mesomers are non resolvable. Racemic mixture, resolvable. Because you can separate the two components of it easily. I can't say the word easily, but at least you can separate the component, then it is called resolvable. Okay? So, coming back to where we were uh, before racemic mixture, we left one definition after diastereomer. Epimers. Epimers are optical diastereomers, okay, with more than one chiral centers, configuration of all chiral centers in these two diastereomers, configuration of all chiral centers in these two diastereomers is same except at any one chiral center. Okay. For example, if I say glucose had four chiral center. Okay. So if I have another isomer in which three configurations are same, and there is no condition which position should it be, it could be any position, any place, but if three are same and only one different, then they are called epimers of each other. So they are basically diastereomers only, that they are not mirror images, but the difference is only at any one chiral center. That is the only specific things. Okay, so now let us go to calculation of number of optical isomers. If a molecule can be divided into two equal halves, that is, it can form mesomer, okay, then the number of enantiomers is 2 raised to power n, where n is number of chiral center or optical stereogenic centers in the molecule. Okay, so if a molecule has n number of chiral centers and is incapable of meso, then total number of enantiomers is 2 raised to power n, and total optical isomers is also 2 raised to power n. If the molecule can be divided into two equal halves, If the molecule can be divided into two equal halves, say for example, we have done tartaric acid, we can have more chiral center, and yes, it can be divided into two. So if a molecule can be divided into two chiral centers, then there could be two cases. It has even number of chiral center, or it could have a odd number of chiral centers. So coming to if it has even number of chiral centers, okay, then its enantiomer is 2 raised to power n minus 1. For tartaric acid, this is 2 raised to power 2 minus 1, that is 2 raised to power 1, 2. Okay, mesomers are this. So for tartaric acid, 2 raised to power 2 by 2 minus 1. 2 raised to power 0, that is 1. So it has one mesomer and two enantiomers. Enantiomers will always be in pairs, so minimum value has to be 2. Okay, but this come to this point that when you comment on total number of optical isomers, yes, we are very clear that mesomers have zero optical active. Optical activity is 0. And I have written optically inactive. But when we are asked that the number of optical isomers, then it is enantio plus meso. Because the meso and enantio differ from each other in their behavior towards PPL only, na? Otherwise, there is no difference. So, when you are asked to comment on total number of optical isomers, please mark these words in your brain. Optical isomers E plus M. Optically active isomers only enantio. Optically inactive optical isomers meso. Okay, so then you have to give it total. If I go to something that is having odd number of chiral centers, okay, then if I take n equal to 3 as we have drawn upside, enantiomers are optically active stereoisomers, then E is equal to 2 raised to power 3 minus 1 minus 2 raised to power 3 minus 1 by 2. So this is 2 by 2, that is 2 raised to power 1, that is 2. Okay, so 4 minus 2 will make it 2. So I'll have 2 enantiomers. See, mesomers. So if n is 3, then m meso is 2 raised to power 3 minus 1 by 2. 3 minus 1 is 2, 2 by 2 is 1, 2 raised to power 1, that is 2 mesomers. Again, total optical isomers you are asked. Then it is E plus M. Okay, so for n equal to 3, 2 raised to power 3 minus 1 E plus M, 2 raised to power 2, that is 4. Total isomers are of 4. Out of this, 2 are meso, 2 are enantio. Okay, so we'll end our discussion of optical isomers here. And I hope it is of basic use towards J syllabus. As usual, repeat your notes. You don't have direct optical isomers question in NCRT, so you have to depend on our modules, Sri Chaitanya Icon Material modules. Please solve those. Go through questions from those. Revise your class notes and study the material given by your respective teachers and apply the concepts. It is a great pleasure to help you understand these all important topics for IIT JEE. Keep watching, keep working hard, and be healthy. Thank you, everyone. See you tomorrow.